Okay. Good morning, everyone. Can you guys hear me?
Yes, sir.
Yeah. Okay. So I'll start sharing my screen. Can you see my screen full screen?
Yes, sir.
Yeah, good. So let's start. Okay, so this is where we had stopped last time. We'd asked whether emission lines, how does one tell whether a emission line in a spectrum of a central region of a galaxy is coming from an AGN or from a non-AGN source. And we said that there is a difference in the sense that the non-thermal emission from AGNs does not have the kind of cutoff that you see due to the Lyman limit of helium in the spectrum of the galaxy. And because of this, the ratio of collisionally excited lines to those lines which are produced in the course of recombination is larger in the case of an AGN-like ionizing radiation field. Okay, so we said that yes, there should be the collisionally excited lines should be stronger in AGN type sources relative to the recombination lines like H alpha, H beta, and so on. Right. So,
Sir,
yeah.
sir, I didn't understand this second half. Like, as a consequence, we get more collisional excited. Can you explain what that means?
Yes. See what happens is if you have a star, right, which is emitting light, right? That light gets absorbed. And where does it get absorbed? It gets absorbed by the hydrogen and the helium, which is surrounding the star, right? So any of the forbidden lines that get generated in the star, in the massive star, have a tendency to get attenuated by the hydrogen and helium which surrounds the star, right? But in an AGN, there is so much energy getting generated that this hydrogen and helium cannot survive very close to the AGN at high enough densities to absorb, right? So the attenuation of the flux forbidden lines by the hydrogen and helium is very weak or virtually non-existent. Okay. Because of this, what will happen is relative to the H alpha line. See, remember, H alpha line is going to be there in massive stars. H alpha line is going to be there in AGN as well. Okay. But if you take a nearby line like the N2 line, which is a forbidden line, in AGN, that line will be relatively, what will it be? Strong or weak?
Strong.
Strong, right? So it will be strong. And because of that, the ratio of the line strengths of, let's say, H alpha to N2 will be very high in the AGN. Sorry, N2 to H alpha will be very high in the AGN. That's correct, because N2 will be stronger in the AGN. That's all we are saying. And it's relative to H alpha. And I'll come to why one compares N2 to H alpha and not some other line to H alpha and so on. I'll come to that in a minute. Okay. So how does one measure the strength of an emission or absorption line? Have you studied this in any of your other courses, techniques course, for example?
By the area under the curve.
Yes, that's correct. So one uses the area under the curve and one quantifies that by a number known as the equivalent width. So the equivalent width is the area of the rectangle that has the same area as the area under the line. Okay. So you don't then have to be worry about the shape, whether it's broad line, narrow line, etc. You're essentially getting the area under the curve and relative to the continuum, right? Relative to the continuum value. So this is illustrated in this figure so that FWHM is shown. Some normalized intensity is shown so that the continuum has a value of 1, right? And what we are doing is finding the area of the rectangle which has a height between 0 and 1 and which has a width such that the area of the rectangle is equal to the area of the under the emission line. That's the basic idea. So the unit of equivalent width will naturally be angstroms. So you can say this is equivalent width of 50 angstroms, 10 angstroms, 30 angstroms, and so on. So a line which has an equivalent width of 100 angstroms will be twice as strong as a line with the equivalent width of 50 angstroms. Okay, sorry, 100 angstroms will be twice as strong as a line with the equivalent width of 50 angstroms. Okay, so this is how we measure line strengths. Okay, and this technique can be used both for emission lines as well as absorption lines. In absorption lines, you find the area below the continuum and find the width of the line that will give you a rectangle of the same height, going to 0 values. So this was done for the first time in a seminal paper by Baldwin, Phillips, and Terlevich in 1981. And in this paper, they plotted the quantities that you see in this figure. On the x-axis, they plotted the strengths, the ratio of N2 to H alpha in log units. So to take the equivalent width of N2, equivalent width of H alpha, divide one by the other and take the log of that ratio. And so you'll get the X quantity. And on the y-axis, they plotted a log of O3 over H beta. Now, a few lectures ago, somebody had asked me, what do these square brackets mean? I incorrectly told you that they refer to metal lines. That is not true. Actually, they refer to forbidden lines. So both N2 and O3 lines are forbidden lines. Right? Now, it turns out, why is N2 chosen with H alpha and O3 always paired with H beta? Is because the N2 doublet actually straddles the H alpha line. Okay, so it's very, very close to the H alpha line. Similarly, the O3 line, right, at 5007 angstroms, that particular line is very close to the H beta line. And the reason for doing that, choosing these sort of closely spaced lines, is that the spectrophotometric calibration will be the same for the two of them. They're separated by very small wavelength, and the extinction, any dust extinction or any other form of extinction that is occurring will be a function of lambda. And if you choose two lines which are very close in lambda in wavelength, their extinction will also be very similar. And therefore, you won't have any systematic effects. That is why one chooses the N2 line rather than some other line. These are also fairly strong lines in the sense that if you have a bright AGN, invariably you will be able to detect N2 and O3 emission from it. They're also quite commonly seen in spectra from star-forming galaxies. So you'll be able to detect them quite with a high signal-to-noise ratio in many, many conditions. Now, of course, what they found was, as expected, and this is the idea behind the BPT diagram, is that if you have a star-forming galaxy or a star-forming region in the center of the galaxy, you take its spectrum, then the ratio of both of these ratios will be relatively small, and that particular object will lie at the bottom left, towards the bottom left side of this figure. On the other hand, if you take AGN, okay, like a Seyfert galaxy or a quasar, then its ratios will be such that it will lie at the top right corner of the diagram, somewhere over here. And this is exactly what we see, right? So what people did was they went and observed galaxies, right? If you have the full spectrum, it becomes possible to really distinguish between AGN and star-forming galaxies. This kind of expectation is also there in models. So there are models of absorption and emission that can be generated, and these models can make prediction depending on the one of the parameters that you can tweak in these models is the ionizing photon flux density as a function of wavelength. And when you tweak that, you find that if you're ionizing, you have lots and lots of very strong, very large number of UV photons, then the line strengths are such that you will land up at the top right corner of the diagram. And on the other hand, if you turn down the UV photon flux density, particularly below the Lyman limit of helium, then the objects tend to fall, the line ratios tend to fall at the bottom left corner. So this is not just purely empirical. From theoretical considerations also, one expects this kind of separation. So what Baldwin, Phillips, and Terlevich did is that they took a few AGN and a few star-forming galaxies that they knew about, and they plotted them on this diagram. And they said just by measuring these line ratios, you will be able to separate the star-forming galaxies, or the H2 regions really in these star-forming galaxies, from the AGN. Now, so this particular plot is from a paper by Trui et al. 2011, where they have plotted this diagram. Now, because of these three authors, this diagram came to be named as the BPT diagram after Baldwin, Phillips, and Terlevich. And here they've plotted 240,000 galaxies from the Sloan Digital Sky Survey. And they've shown the AGN-like spectra with red color. They've shown the star-forming H2 region type spectra in the blue color, and in the gray color they've shown spectra where it is not absolutely clear whether something is a star-forming galaxy or it's a AGN. So these objects are today referred to as composite objects, which is something which has the characteristics both of a star-forming region as well as some emission from an AGN-like source. So how is this possible? This is possible because we know that the AGN can create both kinds of feedback. One kind of feedback, which we call as negative feedback, is where the AGN is so energetic, it simply drives away the gas that from the central region. And because of that, no further star formation is possible, at least in the central region of the galaxy. But on the other hand, there are situations, especially when the AGN is not emitting so strongly. In those situations, it is possible that the energy from the AGN actually compresses the gas that is there in the region surrounding the AGN. And because of this kind of shock compression, the gas begins to form stars because it reaches high densities and so on. And both of these are possible. So in some cases, star formation and AGN, in these cases where positive feedback operates, star forming regions and AGN can coexist. Now remember, for distant AGN, we are not able to probe the region, the sort of milliparsec scaled region of the accretion disk, right? We are probing typically 1 kiloparsec or 2 kiloparsec size regions. So we are probing, of course, the AGN, but we are also probing the stars or the star forming regions well outside the AGN. So these objects, so if you have a star forming galaxy, which strong star formation at the center, then you can of course have a composite AGN in many cases. So the composite AGN region is indicated by line strengths that lie within this zone, and AGN are here and H2 regions are here. Now, this is all fine. We have spectra for 240,000 galaxies. So even without a BPT diagram, we could have looked at each spectrum and figured out whether it's AGN or a star forming galaxy. But getting spectra is expensive in terms of telescope time. So the question is it possible to separate AGN and star forming galaxies without obtaining a spectrum? Does anyone know of any technique where you can tell whether an object is AGN or a star forming galaxy just by looking at images without taking a spectrum?
Sir, I think in AGN there are jets.
Yes, so that is true. So in AGN, if you see jets, you would be able to do it. But remember, jets are usually seen easily in the radio bands. There are only very few galaxies which will show you AGN in the optical and X-ray bands. So now, is there something else that you could use to separate them?
Sir? Yeah. The narrowband imaging. Maybe.
Narrowband imaging is another way. But so, for example, if you have H-alpha imaging, right? Depending on the distribution of the thing, you could take a guess whether something is an AGN or something is a star forming region. If it is very diffuse and spread out, it's obviously a star forming region. If the emission is coming only from the center, then you say, look, it has to be an AGN. Yes. But is there something else? Can you use infrared observations in some way?
Hello, sir.
Yeah.
Sir, regarding infrared observations, I think star forming regions, the infrared flux will be very low as compared to AGN.
Yes.
So by looking at infrared pictures, we can distinguish between the AGNs with the strong intensity in infrared as compared to star forming regions.
Right. It also depends a little bit on whether the AGN or star forming region is dusty or it is non-dusty, because very often infrared emission is strong in dusty conditions, but in non-dusty conditions, infrared emission can be quite weak, and in that case you can't use the infrared. But recently meaning within the last decade or so, a new mid-infrared telescope called WISE has become available. It's a space-based telescope, and by using colors, which means the relative fluxes in different WISE bands, one can actually determine quite well with a high level of accuracy objects which are AGN, objects which are spirals, ellipticals, okay, and even starburst galaxies. So the objects that we really want to separate are probably the ones marked in black, which are AGN, right? And objects marked in blue, which are these starburst galaxies. Okay, and as you can see, there is quite a clean separation. Of course, this is I mean, this separation looks artificially clean because they have in this paper they've simply labeled objects which are within a region of color space as AGN and as starburst. So the real separation is not so clean, but nevertheless, it's a very, very effective way of separating just by using the W1 minus W2, which is, there are 4 Wise bands at 3.4, 4.6, 12 and 22 microns. So you ignore the W4, take W1, W2, W3 and construct this color diagram. And if you do that, the AGN and the starburst galaxies or the star forming galaxies separate out pretty cleanly. And WISE telescope has done an all sky survey. So long as the relevant galaxy is sufficiently dusty and sufficiently nearby, because the WISE telescope all sky survey is relatively shallow. It's not very deep. So you can't do this to separate starbursts and AGN at redshift 5. Okay. But you can do it at redshift 0.1 or 0.2 quite effectively and quite easily. So this has now emerged as a new technique for identifying candidate AGNs. And there are a lot of papers in the last 10 years which use WISE colors to separate star-forming galaxies from AGN. This one also has the added advantage that if a galaxy is particularly dusty, so if you have a type 2 AGN, which is generally more dusty than the type 1 AGN, you are more likely to pick them up here, even if they are relatively faint in the optical. They should be quite bright in the mid-infrared bands, and these objects, which would be otherwise be missed in optical surveys, get picked up in these WISE selected samples. Okay, so now different people proposed different kinds of modifications to the BPT diagram. And they did that primarily by changing which line they were using on the x-axis. Okay, so this is log N2 over H alpha, which was the original BPT diagram, wherein you separated AGN, H2 regions, and composite galaxies. Then other people said, no, let's not use N2 over H alpha, let's use S2 over H alpha. This is the sulfur line. And then they were able to separate galaxies into 3 populations. Seaford galaxies over here, and something known as liners over here, and H2 regions still, of course, remain in this corner. What are liners? Liner is an acronym for low ionization nuclear emission line regions. Okay, so we know that Seaford galaxies or quasars, etc., have nuclear emission line regions, right? We are seeing emission lines from the nucleus for all of these objects. But typically they have high ionization species. What does one mean by high ionization? Which means you won't have, you will have emission from the sort of O1 line, won't have very strong emission from the O1 line, but the O3 line will be very strong. Okay, which is doubly ionized oxygen will be more strong than the neutral oxygen or the singly ionized oxygen. So those are the high emission line nuclear emission line regions, high ionization regions. But there was a class of objects that did not show those high ionization species at all. So for example, it will not show the O3 line at all, but it will show some low ionization species quite clearly. And then you can use other lines like S2 to actually separate in this modified BPT diagram the liners from the Seyfert galaxies. So what are liners really? Liners really are the low energy counterparts of even Seyfert galaxies. We said that Seyfert galaxies are the low energy counterparts of quasars. Liners are the low energy counterparts of Seyfert galaxies. So the emission lines are there, right? They're sufficiently differently organized than the H2 regions. They're sufficiently different from the regular AGN like Seyferts. But so it's really, one can think of liners as something that is intermediate between the star-forming galaxy and the AGN. And truly they are like that. So there is possibly AGN that is active, but it is very weak. So its energy output is very low. There is also very likely star formation also going on. Because liners have these very weak emission lines, they cannot be detected to very large distances, right? So a liner, all the liners that we know of today are at redshifts below 0.1 or maybe 0.2 or so. So one should think of these liners as some objects which may be either switching off, where the AGN has gone down with time, or they're turning on. So maybe the liner represents a transition phase between the AGN and non-AGN mode of a supermassive black hole. That is one explanation. The second author on this paper that I've taken this figure from, Lisa Cooley, is one of the pioneers of studies of emission line galaxies using the BPT diagram and modified BPT diagrams like the one you see here. Both the previous paper, this one and this one, use data from the Sloan Digital Sky Survey. Before the SDSS came along, the numbers of galaxies that you had in each of these different categories was relatively small, so it became a little bit difficult to separate them from each other. But now with literally thousands or even hundreds of thousands of objects in the figure, one is able to plot, instead of individual objects, one plots density contours of the objects. Right. So far in the syllabus, we've covered about roughly the first part of the syllabus. So we've covered the phenomenology of quasars, both radio loud and radio quiet. We've talked about optically violently variable objects. Then we've talked about BL-lacs and blazars. And of course, optically selected quasars. That should be selected is missing there. And we've talked about Seyfert galaxies as the low energy counterpart of quasars. We will now move to the study of radio emission from AGN, which is a subject matter by itself. So if you look at the syllabus says one should study the phenomenology of AGNs, which is what I have done. Seyferts, quasars, radio galaxies is what I'm going to do next. Talk briefly about liners and BL-lacs as well. And then we looked at the continuum characteristics of AGN. We looked at the broadband SED going all the way from radio to X-ray or gamma ray, but we also looked at in a little more detail the features, emission and absorption features that are seen in the spectra of quasars. What remains to be done, which will be done in the rest of the course, is a little more focus on the black hole and accretion disk models for AGN. Then something about the emission line regions. So it turns out that emission lines that we see in AGN are of two kinds. We already know that there are broad lines and narrow lines. So it turns out that the broad line emitting region is spatially separated from the narrow line emitting region. And we look at that in the context of the unification model for AGN. And then we'll also talk a bit about the physics of jets and hotspots. And as I said, the jets and hotspots are most commonly seen in the radio band. So we will discuss all of that in the context of radio observations of AGN. Okay, so now let us talk a bit about radio galaxies. You know that a typical stellar spectrum is a black body. Here is the Planck function plotted at different temperatures, different surface temperatures of the star as a function of wavelength. We can replot this figure as a function of frequency on the x-axis, right? And so this is the black body spectrum as a function of frequency, again, for different surface temperatures. Now, in the 1950s, when for the first time we began to observe the galaxy at different radio frequencies. So a large number of radio telescopes got built in the 1950s, and they operated at different frequencies. And they were able to study the emission from our galaxy at these different frequencies. And they were, towards the end of the 1950s, able to make this kind of plot, which is the intensity on the y-axis and the frequency on the x-axis. This is the spectrum of galactic radio emission. So what does this mean? This means emission coming from the galaxy as a whole. In one of my early talks, I showed you the radio image of the entire sky, and we saw that that is dominated by light coming from the galaxy, from the disk of the galaxy, because there's a lot of star formation happening there. Of course, you see the center of our galaxy and a few other bright radio sources like Centaurus A, but you can measure this kind of spectrum, okay? And this 1 and 2 simply, I think, indicates different directions in which the spectrum was measured. And as you can see, it's a spectrum that sort of whose intensity goes down as the frequency increases. Now, this was particularly surprising because in the early days, everybody believed that this must be some kind of black body emission, because we had seen black body emission in the optical, we knew of black body emission in the infrared, all the models talked about black body emission, but it was quickly realized that this cannot be a black body. And why is that?
In Rayleigh-Jean's limit, it should go as frequency square.
It should go as frequency square, right? And why do you want to use the Rayleigh-Jean's limit?
Because radio energies are much less than kT.
Correct. Correct. So since the radio energies are very low, okay, if it is thermal emission, right, you have to be in this part of the curve of the Planck function, if it is thermal, right? And if that is the case, you can't be here because remember, these frequencies are in terahertz. You will have unrealistically low temperatures for you to, for this part of the curve to fall at radio frequencies, right? You have to be cooler than the CMB, which is impossible. So you're lying in this part of the curve, okay, in the low energy limit of the Planck function, low energy approximation, the Rayleigh-Jeans limit. And here we expect that as frequency increases, the flux or the spectral radiance, as it's plotted here, increases, right? We don't see that. We see as frequency increases, the intensity of the function decreases. And this was quite unambiguous proof that the radio emission that we are seeing is predominantly non-thermal in nature. The word non-thermal is a little confusing because there are thermal emissions in the radio and so on. So one should probably say non-black body type emission. And then people started looking for the dominant physical mechanism for the continuum radio emission that we see. And this was already known from experiments in particle accelerators and so on, that there must be emission, which is now known as synchrotron emission, wherein if you have relativistically charged particles in a magnetic field, okay, you know that even non-relativistic electron, if it is put in a magnetic field, its velocity in the direction of the field doesn't change, but it experiences QE cross B kind of force that causes it to go in a circular orbit. And since its speed in the direction of the magnetic field doesn't change, okay, along the field line, it travels along the field line in the shape of this kind of helix, right? In a helical pattern. And of course, any charged particle that's accelerating must emit radiation, which it does. So it emits photons periodically. As it emits photons, it loses energy. Now, in the non-relativistic case, the emission is known as cyclotron emission. If the electron is moving at relativistic speeds, we refer to it as synchrotron radiation. So what are the requirements for synchrotron radiation? A, there have to be relativistic charged particles. Electrons are the easiest, lightest objects, therefore the easiest to get to relativistic speeds. And there has to be the presence of a magnetic field. And in such situations, you will see emission from that object in the form of synchrotron radiation. So what are the kind of astrophysical locations or objects wherein you will have synchrotron emission?
And neutron stars?
Yes, that's absolutely right. There is a strong magnetic field there, no doubt. And the jets that emanate from the poles of the magnetic poles of the neutron star, they do accelerate particles to relativistic speeds. So certainly there is synchrotron emission from pulsars. Anything else? What about supernova? Will the supernova produce synchrotron emission? Does supernova produce relativistic charged particles or not?
Yes, obviously.
Yes, yeah, there's no problem with that. What about magnetic field?
If there is no problem with the orientation of the magnetic field, how the magnetic field is oriented,
Yes.
then even if the star goes supernova, so there should be no problem in producing synchrotron emission.
But where is the magnetic field coming from? Is it the magnetic field of the star, or is it the magnetic field of the interstellar medium?
Think magnetic field of the star.
Star itself, magnetic field, when the star explodes, the magnetic field will stay in place.
Yeah, I don't know about that. What will
Okay,
happen?
actually not. It is the magnetic field of the interstellar medium or intergalactic medium. So we know now from various observations that the magnetic field is non-zero in both, not just the interstellar medium, which is within the galaxy, but even in the intergalactic medium, there is a magnetic field that we can measure. And because of that, there is no problem with having synchrotron radiation. There is another kind of radiation that is commonly seen along with synchrotron in all kinds of radio situations, and that is called thermal Bremsstrahlung. Okay, this is the so-called breaking radiation. So if you have a plasma in which there is a proton over here and electron is coming close to the proton, close enough to be affected by the electric field of the proton, then it changes speed and direction, and this acceleration of the electron causes it to emit a photon. This is known as free radiation because these are free particles. They're ions in a plasma. They're not individual objects. Thermal Bremsstrahlung is seen very commonly in the radio, either at higher frequencies or at higher densities. At lower densities or at lower frequencies, right, you primarily see the synchrotron radiation. Okay, so we'll talk mostly about synchrotron, not about the thermal Bremsstrahlung. Okay, are there other astrophysical situations where we looked at supernovae, right? That will emit synchrotron. Pulsars naturally will emit synchrotron. Anything else?
Accretion disk around a black hole, maybe.
Yes, that does emit both thermal and synchrotron. What about the jets? The jets that you see coming out of radio galaxies, they also emit synchrotron because the jet is collimated by the presence of a magnetic field. When we look at jets, we'll see how that happens. But there is magnetic field, and of course those jets, just like material flowing out of the pulsar is relativistic, the material flowing out of the accretion disk in the form of jets is also relativistic. And because of that, you will get synchrotron emission from radio jets. Anything else? Have you heard of microquasars? So microquasars are objects where there are two stars which are in orbit around each other, and those stars will if they come close enough, once the Roche lobe of one of the stars fills up, it'll start accreting matter onto the other star. It'll form a small accretion disk around that other star, and the exact things that you see at much higher energies in the accretion disk of quasars, you will see as a accretion disk of this binary star pair, and that is referred to as a microquasar because you see all the things that you would expect to see in or not all, but some of the things that you expect to see in a quasar, you see happening around a star, but at very low energies. So there also you have a magnetic field and the emission coming from relativistic charge particles. Okay, so I'm just going to just show a few formulae now that will illustrate the properties of the synchrotron radiation. The synchrotron radiation has a characteristic frequency, okay, And that is dependent on a few fundamental parameters like the speed of light, the mass of the electron, and the charge on the electron, and so on. But it's primarily dependent on how fast the electron is moving, which is captured by the Lorentz factor gamma, and what is the strength of the magnetic field. So naturally, it turns out that if the particle is moving at higher Lorentz factors, then the characteristic frequency will be higher. If the magnetic field is stronger, then also the characteristic frequency will be higher. Okay. Now we know for a fact that with a typical radio telescope operating, say, at 1 gigahertz, we are able to detect synchrotron radio emission. Now, how high does the Lorentz factor have to be for this radiation to be seen at this characteristic frequency, assuming typical IgM magnetic field strengths? Does anyone know what is the magnetic field like typically in the intergalactic medium?
Ten to the power 3 to 10 to the power 4. Gauss.
Sorry?
10 to the power 3 to 10 to the power 4 Gauss.
No. That's too strong. Okay. It is of the order of micro Gauss. Okay. It's typically a few micro Gauss. So for this problem, if you take it as, let's say, 1 micro Gauss, right? How will you get, at what Lorentz factor gamma will you get emission at 1 gigahertz? You can take it at 4.2 gigahertz if you want, characteristic frequency. That will make it easier. So you just use this, plug in 1 micro Gauss over here, right? That will cancel with this 10 raised to 6, and you need 4.2 on the other side. So this 4.2 is also gone. So gamma square must be equal to, this is in hertz.
Ten to the power 9.
Gamma square will be 10 to the power 9. So gamma will be
10 to the power 4.5.
Yeah, 10 to the power 4.5. So gamma has to be above 10,000, right?
31,622.
Yes. So very, very ultra relativistic kind of situation. And of course, I mean, if the magnetic field is different, the characteristic frequency is different. And it's not that it emits only at the characteristic frequency, right? The characteristic frequency tells you the place where there is maximum synchrotron or the maximum number of photons emitted, maximum number of energy emitted, right? The synchrotron power radiated by a single electron is given by this expression. And again, as you can see, there is a dependence on gamma square like before, and there is a dependence now on B square. And so naturally, if you, here, the dependence is symmetric. So doubling the strength of the magnetic field will have the same impact as doubling the gamma, right? Whereas in the previous expression, for the frequency, it had a stronger dependence on gamma than it had on the strength of the magnetic field. So if you want, this must have already been covered in your electrodynamics course, but the book by Rybicki and Lightman, although quite old now, is still the standard text for understanding of radiative processes. Okay, so now there is also a phenomenon known as synchrotron self-absorption, which is also very commonly seen in radio sources. So if the intensity of synchrotron radiation becomes very high, then the reabsorption of radiation itself becomes important, right? And this will, of course, modify the spectrum of the source at low frequencies. At high densities and at low enough frequencies, this synchrotron self-absorption becomes important, and part of the radiation absorbed by the relativistic electrons along the propagation path will modify the spectrum. This is analogous to what we see in the sun, right? In the sun, we see that photons are, of course, emitted everywhere from inside the sun, but the photons that are emitted inside the sun have a very, very high probability of getting scattered, absorbed by the other material in the sun, other electrons in the sun. So this is the same thing that happens. If the density is sufficiently high, then the brightness temperature becomes comparable to the kinetic energy of the electrons, right? And therefore, it measures. There is a tendency for the photon that is emitted by the accelerating electron to get absorbed, to scatter off another electron and get absorbed, right? And then there is, so just like in the sun, the photon that is created in the center of the sun can never escape outside. Similarly, in a relatively high density or at low frequencies, an electron, a synchrotron photon that gets generated cannot escape to the outside world and therefore gets self-absorbed. So that leads to a turnover in the synchrotron spectrum, as we shall see in a minute. So this is what happens, that in the optically thick regime, the spectral index is 5/2, right? And as beyond a certain frequency or above a certain frequency, the spectrum turns over and there is now a nu raised to minus alpha dependence. Unlike this quantity 5/2, which can be theoretically calculated, in the optically thin regime, the spectral index can vary quite a bit, but generally it is steeper than 0.5. So alpha is greater than 0.5 in this equation. Note that both axes are plotted on a log scale. So now, remember, every electron need not have an emission spectrum that is identical to the other, because their energies, their individual energies are not the same. They're moving at different speeds. They have consequently different kinetic energies. And if you assume a power law distribution in the energy levels of the individual electrons, then it can be shown that the resultant synchrotron radiation obtained by summing up all the individual emissions from different electrons is also a power law in the optically thin regime. Okay, so if you look at an image, so this I've just shown you a part of an image, a very large survey that I had done some years ago to look at some of the deep fields in the radio band. And if you look at the radio band, radio image. So this is an image of a fairly large portion of sky. I think it's about 1.5 degrees this way and about a degree this way. And you can see that there are a lot of individual sources. So each of these black points is a radio source. Some of them are point sources, which means they don't look extended. They look quite small. They're not really points because they're affected by the synthesized beam of the GMRT interferometer. And whereas there are some other sources like this one, for example, which is quite large. And additionally, we notice that there seem to be two objects which are similar in brightness, which are close to each other, right? Similarly, if you're able to observe here, there are two objects which are similar in brightness, close to each other. Over here, I don't know whether you can see it at this level, but over here where my mouse is, you should see two dots which are very close to each other. Similarly here. So about maybe 15, 20, 30%, depending on the frequency of observation of sources in the radio sky seem to occur as either extended sources or both as extended sources and in pairs. This was realized quite early on in 1950s, and this is when the first radio galaxies were discovered. Before we go on to radio galaxies, this is something that I intended to show earlier, but I missed, so I'll show it now. So suppose you take a radio image like this one. You would think that certain regions, like for example, this region is devoid of radio sources, this particular square. But in reality, it's not, because there are sources there, but they're just buried in the noise. So what can be done is that if you know that there could be a source there, you can take a very large number of sources of a class of sources. So the class of sources that I had chosen was quasars. Okay, so suppose there is a quasar here, imagine. I'll make a little cutout around that object. Now let us say there is another quasar here, which is again not seen in the radio. I make another cutout over there. Now suppose there's a third quasar in here, and I make another little cutout over there. And then I stack all of these individual cutouts. And if I do this for hundreds or thousands of objects, then I begin to see the radio emission from that class of objects at an average level, even if the individual object is not detected. So this is the case with optically selected quasars from the SDSS, where you, for most of them, 90% of them, you don't see any radio emission. But if you stack radio images, blank sky radio images at that position, you will begin to see the emission from the quasar. And this is what is seen here. So this is a stack at 200,000 quasar emissions. The radio data comes from the VLA first survey. And here you see clear-cut evidence of a point source. And these arms that you see, this sort of diffraction spike-like pattern, is coming from what is referred to as the dirty beam of the interferometric telescope. So when you study, when Ruta talks to you about interferometry, she will talk about the dirty beam and the process called cleaning, which is used to remove the effects of the dirty beam. So the reason the dirty beam is seen here, although the images themselves have been cleaned, but they have not been cleaned to such depths. So at very, very faint levels, you are able to detect radio emission from quasars, even when the quasar itself cannot be detected, but the average properties can be detected. And this is at the level of 10 microjansky, 20 microjansky, and so on. Very, very faint flux levels. And the reason we are able to do that is because when you stack images together, the radio, the noise at adds randomly. Remember, noise is by definition random. So if you add lots of just random noise many times, right, you will not going to get a signal. But even if there is a weak signal, the signal adds. It doesn't cancel each other out like the noise does. And by averaging over many thousands of images, we are able to detect very faint radio emission. So so it turns out that the sort of radio detections are useful, but blank sky in a radio image is also useful for certain kinds of studies. Okay, so now we'll come back to radio galaxies. This is what are the main features of a radio galaxy. This is a radio image of one of the nearest radio galaxies, which is called Cygnus A. Cygnus A is not a particularly big radio galaxy. We'll look at examples of bigger radio galaxies later, but it does show the 4 main features that you expect to see in radio galaxies. Not all of them are present in all radio galaxies. Some of them can be missing. In fact, here I can't even see the jet very properly, but there is supposed to be you see this spot? That is the core. That is where the AGN is sitting. And there is a jet which is coming out in this direction. And sometimes you see jets in both directions. Sometimes you see jets in only one direction. And the jets end in 2 enormous blobs of plasma, which are referred to as the radio lobes. And in some cases, not always, you see the radio lobe to be brighter in a certain part. The higher brightness is indicated here by red colors. So that is referred to as a hot spot. Hot spot because it is brighter or more intense, right? Similarly, there's a second hot spot over here. These are the main morphological features of a radio galaxy. I'm going to stop now, and the next time on Monday, I will go into more details about radio galaxies and how what they are all about. So I'll stop and take any questions that you have from today's class.
Sir,
Yeah.
do we see these features in all radio frequencies?
No. So I'll describe that in greater detail next time. But in general, you see the steeper spectrum features at lower frequencies. So you will see the radio lobes very clearly at low frequencies. You will see the core, which is generally flat spectrum, that you will see most clearly at higher frequencies. So you don't see everything at all frequencies. Jets are also have a steep spectral index, so you will see them easily at lower frequencies. Yeah, so it's not true that, and so at any given frequency, you will not necessarily see all the features unless the observation is very sensitive. And it will change as a function of frequency. If you go to 15 gigahertz, for example, for this galaxy, you'll probably just see the core. You won't see the lobes at all.
Okay.
No, sir.
Yeah.
So the method of detection, whether it's like Bremsstrahlung or whether it is synchrotron radiation, is by its frequency of emission, right?
Yes.
Okay. And
so, I mean, there are ways in which you can separate the thermal emission in the radio from the non-thermal emission. Okay, by modeling the thermal emission as something that is correlated with, let's say, the H alpha emission. Okay, so suppose you have H alpha emission from the galaxy, then you can model the thermal radio emission as a scaled version of the H alpha emission. And then you can subtract that from the total emission to get the distribution of the non-thermal emission. And the non-thermal emission is generally stronger at lower frequencies than it is at higher frequencies. And there's a simple reason for that, which is the spectral index of the non-thermal emission is very steep, which means that it becomes stronger at lower frequencies. Whereas the thermal emission has a relatively flat spectrum, and therefore it is equally bright in all frequencies. But so that's the reason I said that the hotspot. So the hotspot and the jets, etc., is essentially non-thermal emission. The emission from the core, on the other hand, is a combination of both non-thermal and thermal emission. The predominant source of emission in most of the extended features that you see in radio galaxies is non-thermal. And that can be shown. And again, it's a function of frequency, how non-thermal it is. So it can be shown that at very low frequencies, say 300 megahertz or so, more than well over 90% of the emission is non-thermal in nature.
All right, sir. Sir, and another thing, that is in the BPT diagrams,
Yes.
sir, is the only reason to select to group or to take the ratios between oxygen 3 and hydrogen beta and nitrogen 2 and H alpha is because like these frequency lines are close to each other, or does they have do they have something else?
Yeah.
Like
See, there is
oxygen 3 and
one very important reason is close to each other, but also you need to pick lines that are commonly seen. If you pick a line that is seen only in 1 in 100 objects, in 100 AGN or 100 star-forming galaxies, then that is not very useful because you will not find enough sources to study or to plot on the BPT diagram. So commonly seen, they're commonly seen primarily because they're quite relatively strong lines, not weak lines, even though they're forbidden, and they're very close. So both these criteria have to be satisfied. So there are only 3 or 4 variations on the BPT diagram that are used. So instead of N2, you can use S2, for example, but you cannot use too many more lines because they're too weak to be useful.
Okay, sir. So, and is there any physical significance for like doing these BPT diagrams, or is it just an empirical thing and people just found out that it appears this way, that it forms lobes and like one part and the other part?
So there is a simulation program called Cloudy. Okay, in Cloudy, what you can do is that suppose you have a gas cloud. Okay, you can set its composition. You can say that it's 80% hydrogen, 10% helium, and 5% something else, whatever. You can then set its physical conditions. You can say that, yes, it has this much pressure, this much temperature, this much pressure gradient, this much temperature gradient, etc. You can set its density, right? After that, you can model the spectrum by assuming there is a continuum light source from behind it, right? And that light source you can control. Is it a quasar? Is it a massive star? Anything you want. You can then model what will be the spectrum that you will see after the light passes through the cloud. That spectrum, depending on the physical conditions, could have emission lines, absorption lines, continuum modified lines, and so on. So it also takes into care which transitions are going to happen, what is the probability of the transition. So it takes into account selection rules and so on, and takes into account the chemical composition. So if there is no nitrogen in your cloud, you will not see nitrogen absorption lines. It takes into account temperature and it gives you a spectrum for the whole galaxy. So things are done in a theoretical way using selection rules from quantum mechanics to decide which lines will be seen, what will be the relative strength of the lines, and so on. So all of this, so it is theoretical, but it is not analytic. You cannot write down an equation that will give you the spectrum, but you can model it using your knowledge of gas physics and quantum mechanics to predict the properties of a absorption or emission spectrum. And this is how the BPT diagram can be predicted. So you can construct some source with a certain temperature and give it to Cloudy, and Cloudy will tell you what that will emit at, what is going to be the spectrum of coming out of that particular quasar or star or whatever it is, or cloud, which is externally heated. So everything is done theoretically, but via a computer program rather than a formula.
All right, sir. Thank you.
Okay, I'm sure you'll be introduced to Cloudy at some stage by Shriana. Okay, so if there are no further questions, we'll stop now and meet again at the same time on Monday.